So who am I and what qualifies me to speak on this subject? My name is Michael Tyeska and I have over 15 years of software engineering experience, ranging from a software engineer to DevOps engineer to RPA engineer, data engineer, ML ops engineer, cloud solution engineer. I have tons of experience and have a huge passion for learning new things, particularly in the field of predictive analytics and causal data science. I've implemented some of these features in my app, so I do have experience to implement the tools. And this is from the perspective of an engineer who just has a passion for learning and implementing and building new things. I stand on the shoulders of giants. That means there's a lot of really smart people that have gone before me that have done the work. I don't take that for granted, so I use resources that are available and I build things to apply those learnings. And what I want to do in this series is to share those learnings, share this journey. I invite anyone who's interested in data to, connect and let's take this journey together. Like we're at the forefront of something really new. We're at the forefront of being able to have a lot of data at our fingertips and just really make really good decisions, better decisions to improve our lives. I hope you like this, and then please, if you have any questions, feel free to reach out to me. I'm always open to respond. I'm always open to connect. I'm always open to share ideas and just bounce and learn and just continue to grow. Welcome to our video series on causal thinking and DAGs, specifically tailored to marketers aiming to optimize their marketing strategies. This series will introduce you to the fundamentals of causal inference, essential for making informed decisions and accurate predictions. In Chapter 1, we'll cover the basics of causal thinking and how DAGs helps visualize causal relationships. Future chapters will delve deeper into advanced topics, including Uplift modeling. Stay tuned for upcoming videos that will provide a comprehensive understanding necessary for effective causal analysis and maximizing marketing impact. Understanding causation is fundamental to making informed decisions and accurate predictions. This section introduces the motivation behind causal thinking, emphasizing why it's crucial to distinguish causation from correlation. Causal thinking is essential for various reasons. First, it aids in prediction and decision making by allowing us to foresee the outcome of interventions, thus enabling more informed choices in fields such as healthcare, marketing, and public policy. Additionally, causal thinking helps uncover the underlying mechanisms of observed phenomena, leading to deeper insights and more effective solutions. Lastly, understanding causal relationships is crucial for designing policies and interventions that bring about the desired changes, ensuring that actions taken are effective and impactful. So what are DAGs? A DAG is short for Directed Acyclic Graph. It is a type of graph that helps us visualize and understand causal relationships. The arrows in the graph indicate the direction of the causation, and because the graph is acyclic, it means that there are no loops, i.e., you cannot return to the same node by following the arrow.
Confound it! The batteries are dead!
Confounders are variables that influence both the treatment and the outcome, potentially creating a spurious association between them. Identifying and adjusting for confounders is crucial for accurate causal inference. For example, if we want to study the effects of X on Y, but Z affects both X and Y, then Z is the confounder. Consider the case where a company runs a marketing campaign X to boost sales Y. However, the time of the year Z can affect both marketing campaign effectiveness and sales independently. For instance, sales might naturally increase during the holiday season regardless of the marketing campaign. Let's create a DAG to visualize the scenario and understand how confounders, time of the year, affects both marketing campaign and sales. Okay, so let's take a look at an example of confounders using Python. You will be able to get access to this code. It'll be in the resource section or description or somewhere. We're using the networks package and we're going to create a DAG. You can see here that Z influences both Y and X. And X influences Y. This is another example relative to the marketing example that we discussed. Here we can see time of year influences both campaign and sales, and the campaign influences the sales. We want to avoid confounders. From a purely statistical point of view, such associations produced by them are indistinguishable from the ones produced by causal mechanism, which lead to incorrect conclusions and misguided decisions. By not accounting for the time of year, you might mistakenly attribute the increase of sales solely to the marketing campaign, when in fact it could be due to the holiday season. Let's look at the Python code to illustrate the impact of the confounders. We could take a look at a pair plot. A pairwise plot is a grid of histogram and scatter plots that shows the relationship between the data. The histogram shows the distribution of this variable, and the scatter plots show the relationship between this variable, the time of year, and the campaign, and with the sales. And we can see that there's a positive correlation between it. It's positive because it's going in a positive direction, and there's a correlation because this data is like in a line, straight line. To mitigate the risk of confounding, it's essential to handle variables appropriately in your analysis. This is where the concept of good and bad controls come into play. Good controls are variables that need to be included in a regression model to reduce bias from omitted variables, helping to identify causal effects by blocking backdoor paths. For instance, adjusting for the time of year when studying the effect of marketing campaign on sales ensures that seasonal variations are accounted for, leading to a more accurate estimation of the campaign's effect. On the other hand, bad controls are variables that, when included, can introduce bias. These can be colliders or variables affected by the treatment. Understanding and applying the concepts of good and bad controls is essential for correctly applying causal inference in your analysis, ensuring that the observed associations accurately reflect the true causal relationships and avoiding the pitfalls of misleading conclusions. To illustrate the importance of good controls, let's consider several regression models with different sets of predictors. Let's go to the Python code. And I've already run it, so let's look at the results. The first model, we include only the x as a predictor. This model shows a significance relationship between x and y with an r-squared value at 0.882, indicating that x explains 88.2% of the variability in y. This significant coefficient suggests a strong association between x and y. Let's look at the second model. The second model includes both x and a as predictors. Here, the r-squared value increases to 0.939, showing that adding a explains more variability in y. This coefficient for a is significant, highlighting that a is an important predictor and should be included in the model to accurately capture the relationship with y. Let's look at the third model. In the third model, we include x and b as predictors. The r-squared value reaches to 1, indicating that this model explains all of the variability in y. This suggests that b is highly correlated with y, making it a crucial variable to include in the model. Now let's go to the fourth and last model. The fourth model includes x, a, and b as predictors. The r-squared value remains at 1, indicating that both a and b are significant predictors. Including both variables provide comprehensive understanding of the relationships and helps in accurately predicting y. Now let's take a look at an example of a bad control. In a scenario where we include a bad control, such as a variable that is influenced by the treatment, it may introduce bias. For instance, if A is not a proper control variable, its inclusion may distort the analysis, leading to misleading conclusions. This is evidenced by the skewness and the kurtosis value in the residuals, indicating potential issues with the model specification or data quality. By carefully selecting controls and avoiding bad ones, we can ensure our models are robust and our causal inferences are valid. This practice helps achieving more reliable and accurate results in causal analysis.
If there's a statistical correlation between schizophrenia and an enlarged pineal, why, they may be seeing or feeling what we saw. Their minds may be influenced by those creatures.
Well, how about the hard-on I got? Is there a statistical correlation for that too?
In this section, we delve into why association alone is not sufficient for drawing causal conclusion. We introduce the concept of ladder of causation by Julia Pearl, which provides a structured approach to understanding causal relationships through 3 levels: association, intervention, and counterfactuals. Association. At the first level, we have association. This involves observing relationships between variables without manipulation. Think of it as noticing ice cream sales and drowning incidents both increase during the summer. This doesn't mean one causes the other, they simply happen at the same time due to common factors like hot weather. Moving up to second level, we reach intervention. This is about actively changing one variable to observe effects on another. For instance, suppose you want to see the impact of increasing your marketing budget on sales. By intervening, raising the budget, you can observe any resultant changes in the sales, helping to infer a causal relationship. At the top level, we have counterfactuals. This involves considering what would happen if a different action had been taken. For example, imagine pondering over how sales figure would look if you hadn't run a particular sales campaign, even if you did. Counterfactuals allows us to think about the alternative scenarios and their potential outcomes. Structured causal models help us represent causal relationships using structural equations that describe how variables influence one another. SCM, short for structured causal model, allows for predictions about the effects of interventions and counterfactual scenarios. There are three key components to SCMs. One is variables. These are represented as nodes in the graph and are the elements that you're actually studying. The structure equation, these define the relationships between the variables. For example, you might show how one variable causally influences another. And then the other one is the error term. These represents unmeasured factors affecting the variables. So let's look at an example of an SCM using Python. We'll run the code. All it's going to do is just give us this graph showing that Z influences X, which influences Y. Associations are about observing the relationships between variables using conditional probabilities and structured causal models. For instance, calculating the probability of a customer buying a book A given they bought book B without implying causation. This level of analysis is essential but limited, as it doesn't tell us if buying book B caused the customer to buy book A. Let's look at an example using Python. As you can see, the probability of buying book A given a customer bought book B is 63.8%. Interventions reported by the do operator simulates changes in the system by setting a variable to a specific value and observing the effect on other variables. This concept is essential in determining causality because it allows us to see the direct impact of manipulating one variable on another. For example, in a marketing context, you may use a do operator to simulate the impact of increasing the marketing budget on sales, isolating the effect of this change from other variables. Let's look at an example of intervention using Python. See here we have a simple function where we do some intervention. I'm going to run it. And from this plot, what we can see is this was the original relationship between X and Y. And after we did the intervention, we set X to 1. This is how the relationship between X and Y looks after doing some intervention. Counterfactuals consider what would happen to an outcome if a different action had been taken, even if the action was already taken. This allows for a deeper understanding of causality by comparing actual outcomes to hypothetical scenarios. For example, in a sales context, you may ask, what would happen to the sales figure if this marketing campaign had not run, even if the campaign was already actually executed? Let's look at an example using Python. Here we have a simple function that does some counterfactual, simulating the outcome if a different action had been taken. And as we see, this is the relationship between X and Y. This is the actual outcome, and this is the counterfactual, the relationship between X and Y had we not done this, or had we done some other kind of outcome. In this case, we set it to be 0.
Control, you must bring control.
Statistical control involves accounting for a variable that may influence the relationship between the variables of interest. It helps in isolating the causal effect of one variable on another by controlling the potential confounders. Properly controlling for confounding variables is crucial for accurate causal inference. However, incorrectly selecting control variables can lead to biased results or spurious relationships. Selecting the right control variables can be challenging. Here are some heuristics to guide the process. Domain knowledge. Use your understanding of the domain to identify potential confounders. This involves leveraging expertise and prior research to pinpoint which variables might influence the relationship you are studying. Causal diagrams. Use causal diagrams to visualize and identify confounders. These diagrams help in mapping out relationships between variables and identifying paths that need to be controlled for to achieve the unbiased estimates. Sensitivity analysis. Test how robust your findings are to different sets of control variables. This involves experimenting with various control variables to see if your results hold, thus ensuring robustness of your conclusions. In this video, we've explored the foundational concepts of causal thinking and its applications through DAGs. Understanding causation is crucial for making informed decisions, designing effective interventions, and accurately predicting outcomes. We've delved into the motivation behind causal thinking and the importance of distinguishing causation from correlation, and how DAGs help visualize these relationships. We also discussed the significance of avoiding confounders to predict misleading conclusions, and the critical role of good and bad controls in regression models. The concepts introduced by Julia Pearl's ladder causation, association, intervention, and causation, providing a structured approach to understanding causal relationship. Lastly, we touched on structured causal model, SCMs, and the importance of statistical control in isolating causal effects accurately. Thank you for watching. If you found this video helpful, like, subscribe, and follow me for more content. Connect with me on socials and feel free to leave any questions or comment below. See you next time.